Hello everyone. Lesson number 12 is about light. We'll be talking about the nature of light and solving equations that relate wavelength to frequency. Also, we'll talk about sound and the equation that relate the speed of sound to the temperature. Now, with regard to the light, we say that light has dual nature. And dual nature means that it has both wave properties as well as particle properties. Let's talk about the wave property first, the wave nature of light. Light, like other waves, whether it's water waves, sound waves, mechanical waves, and so on, they have wavelength, frequency, velocity. They undergo certain properties like refraction, diffraction, interference, dispersion, and so on. We'll talk about each one of those in this lesson. Now we'll try to focus on solving problems that involve the wave nature of light. Suppose you turned on your radio and you tuned it to 104 megahertz FM dial. What is the wavelength coming from those transmitting towers? So if we analyze the problem, we are given the frequency, which is 104 megahertz. And if you recall, mega represents 1 million, which is 10 to the power 6. And also we know that the speed of all electromagnetic waves is 3 times 10 to the power 8 meter per second. And radio waves are part of the electromagnetic spectrum, so it will have the same speed as all the electromagnetic waves, 3 times 10 to the power 8 meter per second. So given this information, the frequency and the velocity of the wave, we can use the equation, the speed of light or the speed of any wave, v, equal to the frequency times the wavelength. This is the equation we have to use. Now here we are given the frequency and we are given the speed. We know the speed, so we need to rearrange the equation to solve for the wavelength, and we have to make sure that we write the frequency in hertz. Because hertz is 1 over second, and when you divide the speed of the wave, which is meter over second, by the frequency in hertz, which is 1 over second, 1 over second in the numerator will cancel out with 1 over second in the denominator, and we'll get the answer in meters. So that's why we have to convert frequency from whatever unit you are given to hertz. Here we are given the frequency in megahertz. To convert it to hertz, we have to multiply by 1 million, because mega is 1 million, which is 10 to the power 6. This of course will give you 104 million hertz. And if you want to write it in the power of 10 notation, in the scientific notation, we have to have one non-zero digit to the left of the decimal point. So if you move the decimal point 2 places to the left, you have to add 2 to the 6, and this will give you 1.04 times 10 to the power 8 hertz. If you don't want to convert it to power of 10 notation, that's your choice as well. You can just divide by 104 million, which is 104, and beside it 6 zeros. But when you carry out the calculation, you should get 2.8 meters. And let me remind you here with how to do calculations that involve power of 10. To do calculation that involve power of 10 notation, you have to use the EE or EXP press. So we'll go 3, and then we'll press second comma. This will give you the EE, and it's written as a small lowercase e, then 8. So this means 3 times 10 to the power 8. Recall that the EE press replaces times 10, which is 10, raised to the power. So you are replacing 4 presses by 1 press. And you can go back to our exercises over calculators that we did in the first week of the class. Divided by 1.04 times 10 to the power 8. So we go 1.04 and hit the EE. So that's times 10 to the power. And now we write 8. And we press enter. And as you see, the answer should come out to be 2.88 meters to be exact. So this should be 2.88 meters. Okay, so go ahead and try to solve question number 1 in discussion exercises number 12. Notice here that you are given the frequency of an AM dial, and again AM is a radio wave, so it has the speed of the light, which is 3 times 10 to the power 8 meter per second, and you are given the frequency in kilohertz. So again, you have to convert it to hertz. So you'll be dividing the speed of light by 83,000 hertz, and this will yield the wavelength. And again, here let me show you the calculation. You'll take 3 times 10 to the power 8, so 3e8, that means times 10 to the power 8, divided by 83 kilohertz, which is 83,000 hertz, or we can write it as 8.3 times 10 to the power 4, because 83,000, when you move the decimal point to the left 4 places, it will give you 8.3, and you have to multiply by 10 to the power 4 because you moved it 4 places to the left. And this should yield around 3,614 meters. Okay, a second video will talk about the nature of light and nature of sound. Here in this video we'll focus on solving problems using the equation of wave, which is the speed of any wave equal to the frequency times the wavelength, and also using the equation that enables us to find the speed of sound. Sound depends on the temperature of the medium, because sound moves through compressions and refraction of the medium, unlike light that propagates through the vibration of the electric and magnetic field and hence does not need the medium to carry the light. That's why light can move through vacuum. Sound, on the other hand, requires medium, and the temperature of the medium will determine its speed, because the higher the temperature, the higher the thermal kinetic energy of the particles of the medium. And when the thermal kinetic energy is high, sound will move faster in a high thermal kinetic energy medium. It was found that the speed of sound at 0 degrees Celsius is equivalent to 331 meters per second, which is around 1087 foot per second, or 740 miles per hour. Recall that the speed of light is 186,000 miles per second. So light is much faster than sound, and that's why we see lightning before we hear the thunder. Of course, lightning and thunder happen at the same time, but we see it before we hear it. This is the equation of speed of sound as a function of the temperature. At 0 degrees Celsius, its speed is 331 meters per second. With each degree Celsius, you have to add 0.61, and this is meter per second per Celsius. Notice here that Celsius will cancel out. T here is the temperature, and it's in Celsius. So the answer will be meter per second. So don't let the units confuse you. Meter per second will be the answer to the calculation of this equation. So for example, let's assume that you have a tuning fork that has frequency equal to 250 Hertz, and suppose you set it to vibrate and the temperature of the room was 20 degrees Celsius. What would be the speed of the sound propagating from this vibrating tuning fork? To do that, we have to apply the equation, and when you do that, make sure you multiply the temperature first by the constant 0.61, then add 331. So you multiply 0.61 by 20 degrees and add 331, and this will give you 343.2 meters per second. So we got the speed here. The question is, what is the wavelength? To find the wavelength, we have to use the general equation of speed of the wave, which is the speed of any wave is equal to the frequency times the wavelength, and we rearrange it to solve for the wavelength. So the wavelength will be the velocity of the wave divided by the frequency. Now the velocity of the wave here is 343.2 meters per second. We divide it by the frequency, which is 250 Hertz, and this will yield 1.37 meters. Okay, let's go ahead and solve similar problem here. Determine the wavelength of sound propagating from a 440 Hertz tuning fork vibrating in a 25 degrees Celsius air. Now to find the wavelength, we have to find the speed of the wave. And here the wave is sound. Hence we cannot use the speed of light, which is 3 times 10 to the power 8 meters per second. So what equation should we use? Given the frequency, which is 440 Hertz, and the temperature of the room, T, which is 25 degrees Celsius. Now we know in order to find the wavelength, we have to divide the speed of the wave by the frequency. Now what would be the speed of the wave here? Now one common mistake is the students using the speed of light, which is 3 times 10 to the power 8 meters per second. This is a big error because the question is about sound. Tuning fork will produce sound waves, not electromagnetic waves. So we cannot use the 3 times 10 to the power 8. Instead, in order to find the speed of the sound, we have to use the equation that we just learned. The speed of any sound is equal to 331 meter per second plus 0.61 times the temperature of the room. So basically, we'll be multiplying 0.61 by 25 degrees Celsius and then adding 331. And the 331 is in meter per second. Now, if you carry out the calculation, this should give you around 346 meter per second. So that's the speed of the sound. Now, this is not the answer yet. We are asked to find the wavelength. So to find the wavelength, we can go back to our equation here and plug the values of the speed that we got and divide by the frequency. So the wavelength will be 346 meter per second divided by the frequency, which is 440 hertz. And remember, hertz is 1 over second. So 1 over second here will cancel out with 1 over second. And we'll get the answer in meters, which will come out to be around 0.786 meters. Okay, let's look at more questions here in the discussion. Question number 3, you are given a frequency of the sound wave to be 2000 hertz, and you're asked to find the distance between crest or compressions of the wave. Of course, in the case of sound waves are longitudinal waves. It propagates by means of compression and refraction. So it's basically the distance, for example, between 2 successive compressions, which constitute a wavelength. So we are asked to find the wavelength. And here it asks here to take the speed of sound to be 344 meters per second. So we don't need to calculate the speed of sound using the temperature since it's already given to us. So to find the wavelength, we'll divide the speed of the sound given to us, which is 344 meters per second, by the frequency, which is 2000 hertz, and this will yield 0.172 meters. Okay, question number 4. Again, try to solve it yourself first, and whenever you are done, you can check the solution. Here we are asked to find the wavelength of an X-ray that has frequency of 1 times 10 to the power 18 hertz. Now, X-ray is part of the electromagnetic spectrum. Hence, it has the speed of light, which is 3 times 10 to the power 8 meter per second. So to find the wavelength, we divide the speed of light by the frequency given, and this will yield 3 times 10 to the negative 10 meters. And we expect the wavelength to be very short because X-ray has very high frequency. In the next video, we'll talk about the nature of light in more details. We'll talk about the intensity of sound waves using the unit decibels briefly. And also we'll solve more homework problems. In those homework problems, we'll address several properties of light like reflection, refraction, diffraction, interference, and dispersion. Thanks for watching.